The formation of planetary systems is one of the most fascinating topics in astronomy. Understanding how stars and planets come into existence not only helps us comprehend the origins of our own solar system, but also provides insights into the diversity of planetary systems across the universe. This overview delves into the key stages, processes, and factors that influence planetary system formation. Planetary system formation begins with the birth of a star, which occurs in dense regions of interstellar clouds composed of gas and dust. These regions, known as molecular clouds, undergo gravitational collapse when their internal pressure can no longer counteract gravity. As the cloud collapses, it fragments into smaller clumps, each potentially forming a protostar. As the protostar forms, conservation of angular momentum causes the surrounding material to flatten into a rotating disk known as a protoplanetary disk. This disk is the birthplace of planets, moons, asteroids, and other celestial objects. Observations of young stars, particularly in regions such as the Orion Nebula, reveal the prevalence of these disks, confirming that they are a natural byproduct of star formation. Protoplanetary disks are composed primarily of hydrogen and helium gas, with trace amounts of heavier elements and dust. The disk's structure typically consists of three main regions. The inner disk, closest to the star, where temperatures are high enough to vaporize most materials. This region is dominated by silicates and metals, which later form terrestrial planets. The mid-disk, a cooler region where volatile compounds such as water, ammonia, and methane can condense into ices. This area is crucial for the formation of gas giants and icy moons, and the outer disk, the coldest part of the disk, containing the least dense material. This region may give rise to comets and other icy bodies. The disk's lifetime is relatively short on astronomical timescales, lasting about 1 to 10 million years before the material is dispersed by stellar winds, radiation, and interactions with other stars. The leading theory of planet formation is core accretion, which involves the gradual buildup of solid material into planetary cores. This process unfolds in several stages. Tiny dust grains within the disk collide and stick together, forming larger particles through electrostatic forces. Over time, the particles grow into kilometer-sized objects, known as planetesimals. These bodies are large enough for their gravity to influence nearby material. Planetesimals collide and merge to form protoplanets. In the inner disk, these protoplanets grow into terrestrial planets, while in the outer disk, they accumulate enough mass to attract substantial gas envelopes, forming gas giants. While core accretion is the dominant model, an alternative theory known as disk instability suggests that giant planets can form rapidly through the gravitational collapse of dense regions within the protoplanetary disk. This mechanism may be more relevant in certain environments, such as massive or rapidly cooling disks, where conditions favor fragmentation. As planets form, their orbits are not static. Interactions with the protoplanetary disk and other planets can lead to orbital migration. For example, Type 1 migration affects smaller planets, causing them to spiral inward due to interactions with disk material. Type 2 migration involves larger planets that open gaps in the disk, resulting in slower, more controlled inward or outward movement. Orbital resonances, where gravitational interactions between planets result in stable orbital configurations, play a significant role in shaping the final architecture of planetary systems. As the star reaches its main sequence phase, the protoplanetary disk begins to dissipate due to stellar radiation, winds, and accretion onto the star. This clearing phase marks the end of planet formation and the beginning of the system's dynamical evolution. During this stage, remaining planetesimals may collide with planets, contributing to their growth or leading to cratered surfaces. Gas giant migration can scatter smaller bodies, forming asteroid belts or Kuiper belt-like regions. Interactions between planets can lead to ejections, collisions, or changes in orbital configurations. Modern observations have provided a wealth of data on planetary system formation. Key techniques and findings include protoplanetary disk imaging, where observations with telescopes like ALMA reveal detailed disk structures, including gaps and rings potentially carved by forming planets. Exoplanet surveys, such as missions like Kepler and TESS, have identified thousands of exoplanets, showcasing the diversity of planetary systems and offering constraints on formation theories. Spectroscopy analysis of disk composition reveals the presence of organic molecules, water, and other compounds crucial for planet formation and potential habitability. The formation and evolution of planetary systems are influenced by the star's properties and its surrounding environment. Factors include stellar mass, where higher mass stars have shorter lifespans and more energetic radiation, affecting disk lifetimes and planet formation. The cluster environment plays a role as stars forming in dense clusters may experience close encounters, disrupting disks or altering planetary orbits. Metallicity is another factor, as a star's chemical composition affects the amount of solid material available for planet formation, with higher metallicity favoring the formation of giant planets. The solar system serves as a benchmark for understanding planetary system formation. Key features include terrestrial planets, which formed in the inner disk from rocky material, and gas giants like Jupiter and Saturn, which likely formed beyond the snow line, where ices could condense. Small bodies such as the asteroid belt, Kuiper belt, and Oort cloud provide clues about the disk's composition and evolution. Despite significant progress, many questions remain about planetary system formation, including the exact timeline and mechanisms of planetesimal and protoplanet growth, the role of magnetic fields and turbulence in disk evolution, and the origins of super-Earths and mini-Neptunes, which are common in exoplanet systems but absent in our solar system. Future observations with next-generation telescopes, such as the James Webb Space Telescope, an extremely large telescope, promise to shed light on these mysteries by probing the earliest stages of planet formation and characterizing young planetary systems. The formation of planetary systems is a complex and dynamic process shaped by a wide array of physical phenomena, from the collapse of molecular clouds to the intricate dance of planets in mature systems. Each stage offers insights into the origins of the diverse worlds observed in the universe. By studying these processes, astronomers continue to uncover the story of how planets, including our own Earth, come into being.